Hello everybody. Welcome to this session. My name is Bhaskar Chinni. I'm product manager responsible for time synchronization solutions at Broadcom. Today we are going to talk about some of the challenges in deploying PTP in data center networks and solutions. Amit, you want to introduce?
Yeah, so my name is Amit Oren. I'm from the network switch business unit in Broadcom, and my focus is synchronization and 5G infrastructure.
And my name is Amit Baigawi. I'm a research scientist, and I work for Meta on the PTP and different deployments and different challenges, whatever comes along.
Excellent. Today we will discuss both transparent clock and boundary clock based use cases, the challenges associated with them, and also we will discuss about some deployment scenarios. We have some data from Facebook deployment as well that we will go through towards the end of that session. So, there are we saw several use cases in the previous sessions. PTP used in many different industries, service providers, data centers, power industries, so many industries. But today's focus will be on data center networks. And some of the use cases we listed here. If you have a time synchronized network, then it enables you troubleshooting better, because you will be able to follow the logs easier, how the packet traversed at each hop, and how long the packet, which packet received first, which switch received the packet first, etc. The other use case that other sessions already covered is the distributed database handling in the storage scenario. If the nodes are synchronized with the PTP, that gives 3x performance. So, we will go into details a bit later. And last but not least, if a data center wants to monitor, especially think of a public cloud network where they have to offer SLAs to their tenants, then they need pervasive monitoring, and these days the SLA targets are increasing like 3 nines, 4 nines, and in that case it becomes important you have very close synchronization, very tight synchronization in the network, so that you can gather the statistics with a high precision and then prove that the network delivered the SLA metrics. With that, I will give it to Amit, my colleague, to go into the TC and BC scenarios.
Yeah, so I think the question we want to look at in this presentation is to figure out if a transparent clock is a viable option to deploy synchronization in a data center. I think boundary clock is a well understood method of deployment, and it's been standardized and used in many applications. I think the transparent clock is less well known, and what we want to cover today is some of the characteristics of the transparent clock and whether it's useful as a mode of deployment in a data center. So looking at how a transparent clock is defined in the standards, it's defined as a device that can measure how long it takes a PTP event message to propagate the device. It's also called residence time, and then communicate this measurement to those clocks receiving the PTP event message. So this is a device that's very different from a boundary clock in the sense that a boundary clock terminates the PTP protocol. So on a slave port of a boundary clock, the PTP protocol is terminated, and then on the master ports of the boundary clock, the PTP protocol is originated, and the boundary clock is not a transit device. A transparent clock is a transit device. The sync message that comes out of a transparent clock came in from somewhere else. It did not originate in the device. So that is the main distinction. The standard allows for 4 different kinds of transparent clocks, and they're very, very different from each other. So the 4 variants are 1-step versus 2-step, and a pure delay versus end-to-end delay. So a 1-step transparent clock is one where the measurement of the propagation time or the residence time, which is typically implemented by timestamping the event message on ingress and egress, and just looking at the difference. This residence time is applied to the correction field of the event message itself. So in that sense, the processing is stateless, that I don't have to store the computed residence time, and it's modified on the fly on the event message itself, and forgotten about. Unlike 2-step, where the residence time is not communicated on the event message, and you actually need to wait for a subsequent follow-up message, which may or may not arrive, and correlate that timestamp to the particular flow, because a switch can have thousands of flows, PTP flows, and so you need to find the particular follow-up message and then apply the residence time to that follow-up message. So it is pretty clear that the complexity of implementation varies greatly between these 4 variants. So the simplest one probably to implement from the perspective of the switch itself is the 1-step end-to-end, because that it can be as simple as computing residence time by subtracting 2 timestamps, updating the event message on the fly, and that's the end of it. The 1-step peer-to-peer does require a bit more software. It requires a delay, a peer delay originator and responder, but these typically don't impose a very big workload, because they can be performed like once per second, and so this is not a significant workload on a device. And they have the scalability of almost of a boundary clock. Why? Because every node needs to perform delay measurement to the nearest transparent clock, and we don't have to have a unicast delay measurement all the way to the grandmaster. So from that perspective, a peer-to-peer 1-step transparent clock has the scalability of a boundary clock, because the workload seen by the grandmaster is sending a sync message, which is multicasted all the way to the endpoints. And in terms of link delay measurement, it only has to worry about its peers. And the nodes further away can perform a link delay measurement to the nearest transparent clock. So in contrast, the 2-step variations are significantly more complicated, again, because of the need to process packets in software, the need to correlate timestamps with flows, having to modify packets like the follow-up and the delay response. So these are significantly more complex to implement, and have therefore significantly more delay. And this delay turns out to be a very important factor when we are considering accuracy and and so on. So if we look at in more detail at how this is actually done, the peer-to-peer method of delay measurement basically figures out or measures not just the delay across a node, a transparent clock node, but also of the incoming link into the node. So that if I look at the end-to-end measurement, I have all the delay from the master all the way to the endpoint, which is a sum of delays computed individually by the network nodes on the path, or the transparent clocks on the path, where each transparent clock is responsible for its own delay and that of the link between its peer and itself. In the case of the end-to-end transparent clock measures just the delay across itself, and the residual delay is measured by this end-to-end delay transaction between the endpoint all the way to the grandmaster. So that's the difference. And the grandmaster in this case has to maintain all these unicast delay measurements between, it can be very large number of nodes to itself, and that is the source of the scalability issue. So the peer-to-peer can give you similar performance in terms of accuracy, and also it's a very scalable solution because every endpoint only talks to its neighbor. So who is using transparent clocks, right? So what are some of the use cases that we see? So first of all, a transparent clock is standardized by ITU. ITU, as you know, is mostly concerned about mobile backhaul. It's mostly concerned about synchronization of cellular networks. And the transparent clock, some of the transparent clock use cases have to do with distribution of clocks to cell towers. So one use case that is typical, and we've been involved in that, is a microwave link to a remote tower. The link itself, the two endpoints of the link, implement a distributed transparent clock in the sense that they're both synchronized to each other. They can both timestamp on the same, in a synchronized manner, and therefore the aggregate of the two endpoints with the radio link constitute a single transparent clock. Another very well-known use case is in industrial automation, where the deployment model is one where you have TC plus OC. The propagation of sync messages and is done using the transparent clock, and any node that wants to recover time attaches itself to this transparent clock and performs clock recovery. So propagation of synchronization is done across a chain of transparent clocks, and every local node can recover time being an OC attached to one of the ports of that transparent clock. So one of the goals of Profinet, which is the protocol used in industrial automation, is to be able to achieve better than 1 microsecond accuracy across very long hops, which can be between 30 and 100 hops. And you can see publications of multiple studies demonstrating it as an example here, 200 nanoseconds RMS, which is 0.6 nanosecond peak error across 30 hops, which is consistent with the goals of Profinet. One of the advantages of long chains of transparent clocks versus long chains of boundary clocks is the fact that transparent clocks don't accumulate wonder via the mechanism of gain peaking. If you are familiar with the ITU work, one of the big concerns having to do with deployment of long chains of boundary clocks has to do with the control of gain peaking so that you don't accumulate wonder across the chain, and TCs don't have that problem. So that's why it's very convenient when you're considering long chains. The final use case that we want to look at is TSN. TSN is a collection of standards that one of these standards is called 802.1as, which is the synchronization standard. And this synchronization standard defines something called the time-aware device, which can be, as an example, time-aware bridge, time-aware router, etc. It requires two-step. And they have some similarities to a peer-to-peer transparent clock in the sense that they measure both link delay and residence time. One of the consequences of this mandatory two-step is that these devices typically exhibit very long processing latencies. So the combination of long processing latencies with accurate measurement requires that you perform syntonization, or you understand what is your frequency offset relative to that of the master. And so the solution that they implemented is called logical syntonization, where as part of the peer delay measurement, you also measure the fractional frequency offset between the node and its neighbor. And this allows you to figure out roughly what is your, this is never going to be as accurate as single-digit PPBs that you need in backhaul, but it's good enough for the accuracy goals of TSN, which is roughly a microsecond across 7 hops. So that's good enough for that, and this logical syntonization is actually required. Usage examples of TSN are in automotive and is automotive entertainment and video systems. So I think we talked about the issue of processing latency and the distinction between one step, which tends to be lower latency, versus two-step, which tends to be much higher processing latency. And it's one of the implications of that is on the performance and accuracy of the transparent clock. So a boundary clock doesn't have that issue because it's recovering the clock. It knows the frequency offset of its own local oscillator. TC doesn't have to recover a clock. It's optional. But it's pretty clear that if you have high propagation delay across the node, then your oscillator skew starts to become important and affect your accuracy. And we have a couple of examples here of, if you have 100 ppm offset and a 1 millisecond propagation, then that would imply a 100 nanosecond measurement error. You can improve that by using very common and cheap TCXOs. They typically are 5 ppm offset, and you can improve on the same delay of 1 millisecond. You can improve your error, measurement error, from 100 nanoseconds down to 4 or 5 nanoseconds. So the key, is either to have a good oscillator or to reduce the latency. And reducing latency can be achieved either by using one step, which minimizes the involvement of software in the processing and forwarding of event messages, and also using techniques like providing higher class of service for PTP event messages, etc. So to summarize, we talked about the importance of low latency transparent clock implementations, that these would improve the stability and the performance. And therefore, the recommendation that we would have for anybody attempting to do that is to implement one step, which is much simpler and much lower latency, and also use the features of the switch like classes of service and quality of service to reduce queuing delays, etc. So to try to summarize, the distinction between transparent clocks and boundary clocks, and is a TC a good choice, then we believe that peer-to-peer one-step transparent clocks are just as good as a boundary clock because they have both the scalability and both the performance that is no different from a boundary clock. Again, the key to peer-to-peer is a low latency implementation of the peer delay measurement, because the quick response to a peer delay message, the quick response is just as important as low latency on the sync propagation. So low latency responders are very important. And also, we talked about the scalability, the fact that endpoints only have to talk to their nearest transparent clock. So there's no need to have a unicast link all the way to the grandmaster. So these are definitely a scalable and robust solution to consider for data center deployment. So I think next is you want to talk about some of your experiences.
Sure. Like here we did a test basically now with a open time server as a grandmaster, and then a TC in between, and then an end node. And you can see that the error bound that it adds, there are like 4 layers of transport. It's the same one that goes basically through a snake, and it's still like within plus minus 500 nanoseconds, like for the total push. You can see the Gaussian distribution, while there was also the wander of the grandmaster around the center. So, and this is basically just a picture of the open time server, how like you have a combination of 4 grandmasters, and then they can come in via the first transparent clock that puts them all together. We call it RGSW, and then from there you enter the network. So transparent clocks basically right from the beginning. So call for action, basically again the same thing. We're asking you to come to tap and join us if you have ideas, collaborate, and so on. With no further ado, let's open the floor for questions. Thank you very much.
Thank you. Amit, I have a question. We said that we want to make the PTP a secure service.
Sorry?
A secure service. Any words about the ability of transparent clock in the switch to operate within authenticated PTP message?
Secure service.
Oh, secure. Yeah, I think security depends on how you want to implement it. We've seen requirements that might include MACsec and so on. It's true that there are many ways to implement security with PTP. Some of them have to do with special PHYs that have like fixed latency MACsec and can avoid the issue of having to modify a packet. I think these are available, but it's generally true that if you want to implement MACsec, then you need 2-step implementation, unless you have an implementation of MACsec that is fixed latency, and these exist actually. So I think you have options, right, on how to implement security. Yeah.
May I have the last question, really quick? In your presentation, you mentioned that for the choice, for the synchronization choice, TCXO is good enough with the 4.6 ppm. So my question actually is this: why not just selecting with the little bit better performance, the oscillator, which is better than the TCXO? You do have the option and can provide the better the system performance, right? So what's
Yeah. I mean, so I think in the use cases here that I talked about, we covered a few of them. So that the telecom transparent clock actually synchronizes with the telecom PLL using Sync E. So that is, absolutely accurate, and will fix, all your synchronization issues. But if you cannot afford that, or that you don't have Sync E connectivity in some deployments, as an example, data center may not guarantee that, then, your choices are either logical synchronization, like 1AS is doing, or even a better oscillator. We are all for it. I mean, we never use, Ethernet class 100 ppm oscillators anywhere, right? We don't recommend that, and we don't use that. So yeah, I think you again, you have multiple options ranging from, what ITU is doing to what 1AS is doing. Yeah, there's many options.
Thank you very much, Amit. Yeah, I mean, just to elaborate on that, it's also like from our perspective, it depends also on the residence time and
Okay.
how much you go with.